How did you get to become the guru of tightening?
I didn't realize when I was crushing things in my dad's bench vise, like cutting golf balls in half and crushing Hot Wheels cars like that. I didn't realize I would be actually like training my brain to figure out how a bolt works. And even a small bolt, like an M8 bolt, will pick a car up right off the ground.
That's shocking to me.
And that's one thing we do in here is break bolts, right? We break a lot of bolts in here.
I am pretty shocked at that little drop of sanitizer.
We had a guy putting bolts in his mouth on the assembly line. We've had that sort of thing cause fasteners to break on the assembly line. We had a 10,000 newton meter version of this in the lab recently. It was
10,000
about
newton meters.
10,000 newton meters. Yeah. I want to be careful exactly how the words I use here. I never want to see a torque tolerance tighter than 5%. So this is basically the room here. So it's about maybe 1,500 square feet. Oh, okay. You might want square meters. I'm going to have a hard time with the metric system, I think, in this conversation. But so we've got a couple of cobots set up here.
Okay.
So small UR Robotics cobot set up on a automotive electronics part. We've got a bigger cobot. This is a FANUC 35 kilogram unit for some of the bigger torque tools that we have. This tool right here that's the back end of it. This is the business end of it. This thing is going to tighten 8 bolts at once.
Okay.
So in this case, the customer doesn't know if an 8 spindle will solve their problem. And so what we're doing here is going to test. We're going to test 8 bolts at once to see if it improves the joint quality results.
Okay. You're looking, I assume, for flatness, right?
Yeah, exactly. Yep. So it's really critical that there's so much force being applied by the fasteners that we want to apply it evenly. And the end result is usually much better with a multiple, but it's a big investment. And so testing it ahead of time reduces the risk, and then it also benefits that we already have the programming in place.
Yeah, of course.
So this is a 25 kilogram FANUC cobot. We're tightening this gear here. You see the gear teeth, how big this thing is? Yeah. So this is a circular bolt pattern, and we're basically testing a tool like this guy, and we're going to put this thing into different positions so we can see if we need torque reaction. Over here we have a engine block for like a semi-truck engine. And we've got a 2-spindle rundown tool, and this is the same tool they have in the plant. And then over here, there's a 2-spindle. These are much larger tools. This is for actually doing the tightening of an M18 bolt. Yeah. And so what we're doing there is detection for things like debris in the bearings and things like that. That's kind of what we do on a day-to-day basis. But you know, our name of the game is really helping customers, do the best job of tightening they can, and a big part of that is teaching them about, what a bolt needs to stay tight.
So maybe Jason, let's kick off with a little bit about yourself.
Sure.
What's your journey? As Ryan describes to me, Ryan is the Atlas guy here in South Africa. How did you get to become the guru of tightening?
Sure. So outside of college, I had a job as a test engineer for a tier 1 automotive company that would make suspension modules for cars. Okay. And so we were doing the R&D testing of prototype subframes and subframe systems with servo hydraulic actuators. And we found that we would occasionally come up with bolt problems, right? You would be running a durability test by cycling the suspension back at 1 hertz, and you would find after 20,000 cycles, the bolt would come loose. And what would happen there is we didn't have a lot of resources to solve that problem. So we didn't know, what's the right solution to this. And so I started doing my own investigation, found a real lacking of, in college, we talked about bolts, we talked about bolt preload, we talked about making calculations, but we really never talked about the tightening process. And the tightening process is really one of the most critical things. And now I find that everybody has a shared experience like that, where they haven't really fully gotten an understanding of how to tighten the bolt and what the bolt needs to, how it responds to being tightened so that we can do the best possible job.
Yeah.
And so from that job, I knew there was this area that was unexplored for me, and so I was looking for something closer to home, a job opportunity closer to home, and I found Atlas Copco, and I went in and basically had my first interview here, and I realized that this is a place where I can learn some things. This is a place where there's a lot of cool technology, but also a lot of opportunity to learn some things that I didn't know. And when I came into the interview, I thought we would be testing the tools, right? That seems logical, right? That you would be a test engineer for Atlas Copco, you'd be testing the tools, but the tools really aren't what we're testing. It's the customer product and how to apply the tools to the application. And that was 17 years ago. And so for the last 17 years, I've been doing that here and been doing testing and creating test plans for customers. So kind of taken from the engineering role into a management role and really trying to level up everybody with what I've learned to really help to the benefit of bolts in general. So
Awesome.
really spend a lot of time with teaching bolts and teaching customers what bolts need. Yeah. All right. There's my 5-minute intro.
Yeah. So you obviously have a deep passion for this. I mean, you must have played around with stuff as a kid, right?
Oh yeah. I didn't realize when I was crushing things in my dad's bench fights, right? Like cutting golf balls in half and crushing Hot Wheels cars like that. I didn't realize I would be actually like training my brain to figure out how a bolt works when you crush stuff in a vise. It's actually an excellent analogy for a bolt is that bench vise when you turn the handle and it crushes stuff. Like that's what we're trying to do when we apply a torque tool to a bolt, right? If you got a bolt like this, right? We turn the nut and you are creating a clamp. Yep. And that's really what we're trying to do with this thing. So.
Yep. I mean, at the end of the day, a vise has got a screw in it anyway, and you are actually.
Yeah, exactly. But no one would ever think to put a torque wrench on that handle, right? Yeah. Like you would just feel it, right? Yeah. And so we take it for granted the forces that we're putting in, what the actual end result is on the vise.
Yeah. I actually think you've touched on something. I never thought about it. Actually, when you put something in a vise and you tighten it up, you actually feel, and you get a sense of the fact that it's actually now clamped and you can do whatever you need to do with whatever it is that you're grinding or something, right?
Sure, yeah. And everybody's felt that loosen up on them, like they didn't tighten it enough and they go to grind on something or hit it with a hammer, right? And have found that they didn't tighten it enough. And usually the recipe is tighten it a lot. Yeah. And that's a lesson that I feel as engineers maybe we don't fully appreciate the tighten a lot lesson. I think if you come out of engineering school with this idea of factor of safety, that everything has to have a factor of safety of 3 or people are going to get hurt, and that lesson gets hammered into you, right? But the bolt, like taking a bolt like this. So this is an M20 bolt. So this is a 10.9 20 millimeter diameter bolt measured at the threads. So this is good for 57,000 pounds of clamping force, okay? So it sounds a little scary to take this to, say, 50,000 pounds to generate over, almost 90% of its ultimate tensile strength. It sounds a little scary to an engineer to say, we're going to tighten this bolt to 85 to 90% of its ultimate tensile strength and then ask this bolt to go out in the world and do its job, right? Yeah. But that's exactly what we want to do in many cases. And in the case of like critical engine fasteners where we've got critical joints like we talked about with the maybe connecting rods for an engine or a main bearing cap, like those bolts are all tightened to 90+% of their ultimate tensile strength, and then they go out into the world and do their job.
Yeah, it's crazy. And you just think how many bolts, literally bolts are keeping the world together.
Yes, yeah, absolutely, yeah. When you see like a semi truck going down the road, that engine is getting all of its strength from the pre-stress of all of those fasteners. And so the tension that we generate during the tightening operation is critical to how round the bore is, how round all of the crank bore and the cylinder bore, and then that's actually where the engine gets its strength from. So if you think a big solid engine block, it's getting its strength from the pre-tension of all of those fasteners, and that's really the magic of how the bolted joint works. Is creating that high amount of tension. And just the cylinder head on that diesel engine for a semi truck is generating over 1 million pounds of clamping force.
Wow.
So we're talking about 300 cars worth of pressure holding that joint together. It's quite impressive.
Yeah, I never thought about the fact that when an engine is running, it's actually the bolts taking up the load, and that's being translated,
Yeah, yeah.
through a series
Hmm.
of steps into the wheels, right? And that tension is
Yeah,
actually coming from the bolts holding everything together.
yeah, exactly. Yeah, it's something we really don't fully appreciate when we think about something like that. It allows the shape to be in such a way where you couldn't even make it out of one piece. So
Yeah,
if you had an engine that you could somehow get in and machine all of the areas that you needed to machine and make it out of one billet block of iron, it would not be nearly as strong as it would be if you bolted it together. So
yeah,
just the idea that we're using bolts, we're using threaded fasteners to create this huge amount of tension force, things all around us are getting a positive impact from that phenomenon, and it's
yeah,
it's it's something we don't fully appreciate, and it's happening in the background.
yeah. That's for sure. So maybe we could get a little deeper into, you know, what can go wrong with the bolt? Because obviously, at the end of the day, we all know we need to tighten it correctly, and we'll get into
Yes.
strategies
Yep.
around how to tighten it correctly. But I guess in your training, I would imagine you talk about, what can go wrong.
Yeah. Yeah. So what can go wrong is the primary thing is that friction is different in the joint, and so 90%, approximately 90% of the torque that we put into the joint goes into overcoming friction. And so if we have a change in the friction, this is our number one problem in a tightening operation, is that the friction coefficient of friction changes. So there's friction happening in two places. So if we have a bolt like this, we certainly have friction. We're going to use this analogy like this inclined plane, peel the thread off of here, and then we've got this huge mechanical advantage with the bolt. So if friction changes, the friction, if it's lower, it's going to take less torque to achieve that amount of tightness. And so usually our torque tools are programmed to a certain amount of torque. So what ends up happening is that we get much more clamping force than we anticipate, and then you end up often with a broken bolt. So you tighten the bolt down, and the friction is lower than you expect, and you get much more clamping. And so that's really the first thing that can go wrong. So I've got a little model to kind of demonstrate this. So this is basically the same size bolt, but it has a scale on it.
Okay.
So we can actually read the bolt preload just like you could read a scale like this. Okay, so you've got a scale like this guy right here. So we can tighten this bolt down, and I've got a simple torque tool. Like this is a clutch tool. So this basically, once the torque achieves a certain amount, it will overcome the clutch and shut the tool. Okay. So we can demonstrate with this bolt. So all I've done is taken my little and this bolt has a spring in it, just like a tension scale. You can kind of see that.
Yep.
Okay.
That's very
So
cool.
the torque is going to be really low here, but we're going to take a rubber washer. This washer is pretty grippy, so it's pretty high friction. And when we put it on this joint right here, we can see the clamping force we generate when we tighten this tool up. Okay, so we run this down, and we get about 1 Newton of bolt preload. Okay, that's tension in the bolt. So we should maybe talk about torque and tension and the units that we talk about. So torque is the twisting force. That's a force times that distance, right? But when we talk about bolt preload, this is purely a tension force. So this could be kilograms of force or kilonewtons of force or pounds of force. Okay, we're talking about tension in the bolt. If I add some contamination to this thing, all right, so I haven't changed the setting on this tool at all. But if I take this nut and I back it off and I add just a little drop of something, and this is just a hand sanitizer. It's oil, water would work here. This cleans up really easy. So if I just add, let's see if I can show you this. I'm going to add 1 drop of this on here. Okay. So what we've done is changed the friction in the joint. And so now when I put this same power tool on, what's going to happen is that since the coefficient of friction is lower, the clamping force is going to be high. And so we run this thing down and we see,
Oh my word.
we get we get 6 times as much clamping force. And actually, we didn't even fully tighten the bolt because the socket got pushed off of this thing. So we have the relationship of friction causing a dramatic increase in the variation of the tightness of the bolt. And so this is the number one problem that we see in a factory, is that friction changes affect the tightness of the bolt.
Wow.
So that's the first part of it, right? So I bet that's not something that everybody knows. It's just how much variation we actually see from friction. And this can be in all sorts of different forms. So we see thread adhesive, things like that. I mean, in your industry, you see lots of probably like patch locked bolts that have an adhesive patch on them,
Yep.
right?
Loctite
For usually,
something.
yeah, exactly, some kind of adhesive like that, right? So that sort of thing when you go to repair that joint is going to have a different coefficient of friction than it did when it was assembled the first time. So there's definitely variation that we see there. The biggest problem manufacturing has is making sure things are consistent. And so we'll see oil contamination causing huge problems in a plant, just from inadvertent contamination causing breaking bolts.
Yeah.
And the tools get blamed a lot for that because it's not obvious that the friction has changed. But realistically, what's happened is that the torque is still the same, but the friction is different, so the result is different.
I am pretty shocked at that little drop of sanitizer has had such a significant impact. I've tightened hundreds of bolts on many factories around the world, and I'm acutely aware of the impact of like lubrication on torque.
Mm-hmm.
I did not realize that it's that much. That's shocking to me.
So what's happening? Can I draw you a curve here?
Yeah,
Can
please.
I draw you like a
it.
torque angle graph? So
yeah,
we'll draw like it here. Be good and we can see it. All right. So here we have. All right. Let me move this. Yeah. Here we grab this other angle. Yeah. Okay. So on this axis we have torque, and this axis we have angle. So the bolt is going to go through a couple of phases of tightening. We're going to pull the trigger and we're going to run this bolt down, and the bolt's going to free spin forward, right? Just running down like this, right? So the torque is going to be very low. All right. So this is our rundown phase. Then we go into this seating phase where we start to draw the parts together. All right. So parts are going to connect like this, and we're going to get into this section here, and then this is our linear elastic section. Okay. This is where the bolt really stretches like a spring. All right, and so this is actually the goal of the fastener, is to get into this linear elastic range, and then leave the bolt here in most cases. Okay. Let me ask you a question. Do you remember the stress strain curve?
Yep.
Back from college, right?
Yep.
So let's talk about that for a second. What is stress? So stress is just force over area, right? Right.
Yep.
And so what is happening with the torque? The torque is the amount of force, is a representation of the amount of force on the bolt, right?
Yep.
So if you remember that stress strain curve, we're taking a tensile test specimen and we're pulling it until it snaps, right? Yep. So what's on this side of the curve? We have strain, right? Strain is just change in length over length. And so this is stretch. This is proportional to the angle of tightening, because the angle is on a fixed distance between the threads. So the angle is representative of how much we stretch the bolt.
Yep.
Okay. So if you remember what that curve looks like, this curve is going to look exactly the same.
Yep.
If we continue tightening up this linear elastic curve, at some point we hit this point where the material starts to do this. All right. And then we get fracture.
Yep.
Okay. So this point right here, we call that the yield point, right? I know I'm back 20 years ago in my material science days, right?
Yep.
Okay, so this is the point where we get permanent deformation of material. Exact same thing with the tensile test specimen we're seeing with the bolt. Okay, so what happens when we change friction is we get this happening. Let me pick a different color. We tighten the bolt. We have the same rundown phase, right? But the slope is lower because the friction is lower. So the relationship between how much torque we're generating is it changes the amount of force. So we end up with a slope that looks like this. Okay. And so what typically happens is at a similar angle to where you snugged the bolt down, this angle tends to be pretty consistent to where the yield point happens. But the torque will be lower, and this graph will match this one, but it will fall off like this.
Yep.
Okay? And so for this reason, you have a different amount of torque that it takes to break fasteners. And that's one thing we do in here is break bolts, right? We break a lot of bolts in here. And really, because this leads us to understanding this. So we add a lubricant to it, we get a lower torque value that it takes to fracture the bolt. Now, my target torque is in here somewhere, right? So I'm trying to hit a point in the linear elastic range in most of my tightenings, and then I'm affected by friction. So the highest I can push this torque is the lowest friction condition that this joint is going to see during assembly.
And you're obviously targeting this higher torque, and if you have too much lubrication, well, beyond the design of the system, you end up breaking the bolt.
Yep, exactly. And the first thing you should see if you break a bolt on the assembly line, which really shouldn't happen, we should be able to. So this angle, it takes a lot of angle to actually break the fastener. We should be able to program the power tool so that if it gets to a significant point past where we expect it to, to see yielding, that we reject the part, turn the tool off, give it a red light, and then we kind of philosophically need to embrace the red light and think that that's a good thing. That's a manufacturing engineering lesson that's tricky too.
Yep.
Is that we actually want to set up equipment to detect bad parts, and when it happens, it's not the limit's fault, right? I watched a video you did on this, right, where you were generating limits for something, and it's not the limit's fault. You actually want to identify the bad part, right? You want to say, hey, that's a good thing. That red light's actually a good thing. It told me I detected a part in my factory before it went out the door, because that's the worst time to have it goes out to the customer. So we should be able to set up. Yeah, go ahead.
It's not a fault of the tool.
Right, exactly. Yeah. So you should always be able to program, in this somewhere in here at least, somewhere to stop the process before you end up with a broken. Okay.
I was last week at a customer, I won't say who, and I was looking at it was a force and displacement, it was pressing in a bearing, and the curve is obviously very similar. And the windows were wide open, and I said, why is this wide open? It's kind of, you have all this fancy equipment, servo systems, load cells, all that kind of stuff. And they said, no, they opened it up because it was failing.
Yeah.
So I'm like, what's the point, right?
That's a perfect example. That happens all the time with tightening tools.
Yep.
Yeah.
What's your, so you kind of demonstrated the impact of thread friction, putting some sanitizer on thread friction, and you basically produced that graph. What do you think the impact of underhead friction is? Maybe what is underhead friction and the impact of underhead friction?
Yeah, so if we have a bolt like this, if we're turning the head of the bolt, right, under the head, there's a raised surface under the head. That's going to take up about half of our friction, and then 40% is going to be in the threads itself.
Okay.
So we're going to see that cumulative 90% of the torque we put into the joint going into overcoming friction. So the under the head of the friction is just as susceptible to variation in friction as the threads themselves. So it's really about, if there's a hole in a plate, right? Is that top surface painted? We've seen situations where all they did is change the painting process, and it dramatically changed the results, right?
Wow.
We've seen there's so many different stories. We had a guy putting bolts in his mouth on the assembly line, just like you would do on the top of a ladder. And I'm guilty of this at home, I guess, sometimes, but not every day in a factory. But we've had that sort of thing cause fasteners to break on the assembly line. So it never ceases to amaze me, some of the variation that happens in a factory in the real world. So.
Yeah, factories certainly illuminate the art of the possible.
Yes, that's definitely true. Yeah.
Both in a good way and a bad way.
Yeah, yes. Yeah, and this is why teaching, I think, is so important about this. So just the simple lesson is the friction is the first thing you should look at. I've seen so many times where a hardness test is performed in the fastener before they investigated friction. This is 20 times more likely to be a friction situation than a bolt
Yeah.
hardness test. It's possible that this is actually the lower braking torque is caused by a hardness issue where a heat treatment problem has happened with the bolts, but it's much more likely that it's that's related to friction.
Yeah. And would you say the variation in friction is related more to a manufacturing problem of the bolt, or the surface of the material that you're clamping, or is it sort of lubrication?
It's usually in the handling of the bolts that we see something occur. We're assuming some friction variation. It's actually pretty significant. In one box of bolts, you could end up with a pretty significant variation of just natural variation of the coatings, surface roughness, things like that. That's all stuff we're going to have to handle in the tightening operation. It's the excessive stuff of handling, adding lubrication, just having, dust or rust, those types of things. We can minimize the situation there. We're going to end up doing a better job. So if you could just walk the line and investigate where friction is potentially causing chance for contamination is happening, and putting some things in place there is going to directly improve the results.
Yeah, that makes sense. And those are basics that, unless there's an understanding of the impact, are often not considered.
Sure. Yeah, you could get a new coating of a fastener too. So your supplier could change their coating process, or you could buy bolts from a new supplier, and you could find that just the coating that they're using shifts the amount of clamping force that is the end result of the process.
Yeah.
So this is really why angle monitoring is like the first line of defense from a fastening operation. So monitoring, setting up the tool to monitor a low point in this curve that is somewhere in the linear elastic range, but as low as you can reasonably be, and monitoring the tightening angle. This is going to tell you this is actually going to tell you information about the consistency of the tightness of your bolts. And if you set everybody up, so like this example where I have here, where we're targeting this torque on this one right here, and then this one right here, you can see the blue one has more angle from this reference point, right?
Yep.
So you can infer that a higher tightening angle is equivalent to a higher clamping force because the friction's changed.
Yep. So the impact, if I'm understanding correctly, the impact on that initial torque, the impact of friction, let's say, on that initial torque is lower because it's obviously not so tight.
Right.
And angle doesn't care about friction; it's just going to an angle.
Right. Yeah, almost exclusively adding clamping force to it.
Yep.
There may be a little bit of torsional stress component there, but that's getting into the small details. Okay. Adding additional angle is just adding additional clamp load as long as we're in this linear range. Okay. Yeah.
So maybe we could just recap for those that don't understand torque and angle. You kind of repeated that. So you would maybe just recap what is torque and angle if I were to kind of ask it from the beginning like that.
Yeah. So, well, you're talking about like an angle control tightening process, like for a critical fastener. Yeah. So in most cases, we're just controlling by the torque value, and then we're bound by variation of friction, and that's going to give us a certain amount of variation of clamping force. But actually, we could take this same curve here, and we could create this threshold torque as our torque value, and then we add plus some amount of angle, and we can now are controlling in this axis. And so now instead of tightening this bolt, let's say we can even be higher up in the clamping force. So we could be right before the yield point, and now I could target this torque or this angle, and so I can control by this amount, and now I can get actually a much more consistent amount of clamping force in the fastener because I'm getting additional elastic stretch beyond that snug bolt. And so my mean clamping force goes up, which means I can maybe use a smaller fastener, lighter weight, more efficient, cheaper assembly. And I can get, not only can I get more clamping force, but I can get more consistent clamping force with an angle control strategy. So you might see, you're going to hear me maybe say that angle control. I'm going to say the torque is 30 Newton meters plus 60 degrees, something like that, a spec like that.
Yep.
And so instead of tightening to 100 Newton meters, we're going to do this as a torque plus angle strategy where we're actually controlling by the angle. We're using that 30 Newton meters to get into the linear elastic section of that tightening where we're starting to stretch that bolt and then turning 60 more degrees, stretching it an additional amount, and then we're seeing that we can have more clamp load and more consistent clamp. And that's a huge benefit.
How do designers come up with the 60 degrees?
Yeah, so that's a good question. That starts with, I like to do it with a failure test. I actually like to see what's happening with the fastener. So we like to, if we do a failure test, we're going to get a range like this. We're going to get a bunch of curves that look just like this. We're going to analyze the snug torque where we get that linear range, and then we're going to figure out how much clamping force we want to achieve. So in most cases, we were trying to maximize clamping force. So like if I were trying to assemble this frame behind me, right, I would want these joints to be as tight as possible, right? And so I would want to be close to the yield point or potentially even beyond the yield. So you decide this angle based on the thread pitch and the free length of the bolt. So we call this the effective length, the distance between the underhead to the face of the nut. This distance is essentially the length of our spring. And so it's based on the stiffness of this spring, and it's also based on the compression stiffness of the part. So most of the angle is going to go into elastically stretching the bolt, but some of the angle is going to go in at the same time, going to go into elastically compressing the part. I would estimate 85% is going to go into bolt stretch. 15% is going to go into part compression, but it's a balance of these springs that we have to play with. And so it depends on the parts. To answer your question about how much angle, it depends on how long the bolt is and how squishy the parts are.
Yeah. And you say that, is that something that you guys do? Like a customer says, okay, here's a joint. I think I need a clamp load of, I don't know, 100 newtons or 100 kilonewtons. Sure. Would you then help them establish the right settings for the torque and angle?
Yes, quite often they've analyzed their parts and say we do need a clamping force of X because they know that through their computer modelings before the parts were ever available, they know that I need, let's say, 100 kilonewtons of bolt tension in order for this part to do its job. So we can actually take and do a failure test and do analysis of the curves based on the yield strength of the fastener. We can assume some things about the strength of the bolt and the clamping force that's happening at this yield strength. But beyond that, the best way to do it is actually to make a bolt clamp load measurement using ultrasonics. So we've got a system that puts a sound wave through the bolt. So we excite, there's a chip that we machine the bolt flat, we bond a chip to it, and we send a sound wave through the bolt, and it bounces off and comes back, and we measure that echo, that time for that echo in nanoseconds. We do that in the bolt's loosened condition. Then we tighten the bolt, and the bolt stretches and gets longer, and we can actually measure that change in time, and that is a very good correlation to the tension force in the bolt. And so that utilizing that, we can actually measure bolt preload, bolt tension. We can measure torque, angle, and tension all at the same time and get a curve like this so we can dial the tightening right into the tightness that the customer needs and give them the best possible tightening strength.
Wow, that's pretty cool. So you're using ultrasonics to measure the length of the bolt. So you
exactly.
can measure the stretch basically and then relate that back to the clamp load essentially.
Yeah, exactly. Yep. And we do that by tightening against the load cell and understanding the ultrasonic signal, how much force that's actually generating in the parts. Yeah.
Wow, that's pretty interesting. Maybe a very basic question, because we've come across this a couple of times. Often a bolt is hand fitted on a production line, and there's always a risk of a cross thread at the beginning. And then let's say it's a manual fitment initially, and then it goes into some auto tightening station. How would you manage that?
Yeah, so that part of the process is happening way back here, right? A
Yep.
cross
Yep.
thread is going to like kind of draw up like this, and it seems like a cross thread would be a high friction scenario, and it is high friction, but we actually see the slope of this line being usually much lower than the slope of the actual elastic tightening. And so we'll set up a window within the process to detect, say, the first 360 degrees that we don't want to achieve a certain amount of torque. And so
Yep.
what we're able to do is, this is part of the value of using a high-tech power tool, is that we can set up monitoring through the whole process. So from the moment the trigger is pulled, we can be monitoring the angle and shut down the torque much earlier than getting to the full tightness. And then you've damaged the bolt and the part. Where in this case, you maybe only have damaged the bolt. Maybe it's totally repairable if
Yep.
you're down here at a much, much lower torque.
Okay.
Beyond that, you can actually start off going in reverse if you want to. So quite often in an automated assembly, we'll go backwards first, just like you would put the lid on a jar, right?
Yeah.
Or the cap on a jar, right? You go backwards, you feel
Yeah.
the thread, and then you run it forwards. We do the same thing with fasteners. So we'll do a multi-step tightening where we go backwards first, then seat it to maybe run it 360 degrees forward and make sure the torque isn't too high. And then if that passes, then we'll come up to our seating torque, do a high-speed rundown. We'll shift speeds and go much slower and do a much more controlled final tightening up to our target. And that really gives us the best control over the situation about how we set up a tightening.
Do you ever get involved in, like, let's say, weird kinds of bolts, like a self-tapping bolt? Because I would imagine sort of self-tapping might have a higher initial torque, and then it starts to tap, and then it drops off. And do you have strategies around that?
Yeah, there's really three kinds of things that we have to deal with there. We call this prevailing torque. I think my graph is getting too messy here.
Okay.
So I'm going to kind of start over here. Okay.
Okay.
So we've got all right, let's go back to this color. All right. I'm a big label your axis person. So we got a torque and angle here. Okay. You see what we're dealing with here? So we pull the trigger, and let's say we have a drilled hole, and we have an aluminum part with a drilled hole. This is really becoming a much more common tightening operation, where we have what we call a trilobular fastener. And this is, instead of the cross section being totally circular, it's kind of triangular shape. So if you could picture this part of the bolt, right? Instead of being a circle, it's got this triangular shape to it. And so what it does, the benefit is that it eliminates the machining requirement for creating that tapped thread. Okay. And then also it locks in place. So it acts as like a locking mechanism for the fastener. So if we have a fastener like that, we're going to engage this thread, and then we're going to see there will be a little variation, a little wobble in this curve, but you're going to see a continual rise in this. This is what we call prevailing torque. The torque it takes to run the nut down itself, or to drive the fastener in. And so we're going to see this continually rise like this, and then this fastener is going to seat, and then we'll be able to tighten it and shut it off. Okay. Beyond that, you could have, let's say we're forming into a sheet metal, and you're passing all the way through the substrate. All right. So in this case, we might have a high torque, and then it's going to drop off, and then it's going to seat. In this case, we can set up acceptance windows into the process to make sure that it's above this value and below this value. These are all things we can program into the power tool to make sure that the path is achieving. Just like your force displacement curves, we can do many of the same things with a torque and angle curve. And I imagine you're picturing that, right?
Yeah,
There's that
absolutely.
similarity between those two things.
Yeah.
All right. And then the third thing is basically a flat line, like a lock nut. So if this nut was locked, once we got through the nut, it's going to be flat prevailing torque. I think everybody's seen a nylon lock nut, right? Where there's a nylon ring in there, and then you get it to engaged about here, and then you got to get a wrench to run it down. That would be a flat prevailing torque, and all of those things can be monitored or even compensated for. So to jump topic just a little bit, in the aerospace industry, when we're building aircraft, often we have a flat prevailing torque where we're running down just like this, where there's a lock nut, right? And so the lock nut is running down like this, and then the joint seats and it is tightened. Well, the specification in the aerospace industry is to measure this prevailing torque and tighten to an additional value beyond that. And so we end up monitoring this and compensating for it while the process is running. So it really depends on the industry, depending on how we handle.
What's the logic around that? Because that prevailing torque is, presumably coming from the lock, the nylon lock part. Why would that have an influence on the final torque value, or why should it?
So this is robbing from the final tightness. So if I'm taking this and targeting 50 newton meters, and I have, let's say, 10 newton meters of prevailing torque. All right. Let's say I forget to put the lock nut on and I put a plain nut. What might happen is that it's going to run down at a much lower torque, and then it comes up and tries to hit 50, but maybe stops short. Maybe it can't even get that high, and the bolt strips out. Okay. Or the opposite happens. Maybe they have the wrong nut, or there's damage to the thread, and the prevailing torque is very high, and they run this thing down. Now this is a situation where the clamp load is low, because this torque between the prevailing torque and the final torque is like the amount of clamping torque we're putting into that torque.
Okay.
So variation here affects the level of tightness.
Yeah. So if I understand correctly, they're trying to compensate for the variation in the impact of that nylon part.
Exactly.
In the run-up phase.
Yep.
Okay. Yeah, yep. That makes a lot of sense. You mentioned the drilled holes earlier with the triangular bolt. What are typical applications of that?
I mean, I see it in aluminum parts, particularly like housings and things where there's a lot of holes to drill. Like, so say you have a transmission or like a transfer case, right? Those typically have aluminum housings, and there's pieces that need to be screwed together, right? And so they get a benefit from having the reduced cost of machining and the self-locking that happens in the self-forming faster. So we see quite a bit of that on anything aluminum that we're putting together, like case halves. Even if you were to go to the store and buy a small engine, I would anticipate that the engine, the external parts of the engine are put together with these types of fasteners, because there's such a cost benefit to it.
Yeah, makes sense. I'm trying to remember. I don't think I've ever come across those. I would imagine they're relatively small torques, and like if you have multiple bolts in a housing, like you say. Or do you get
we
very
see
big
it
torques?
in bigger castings too. Typically a small size M10 and under would be typical. Yeah. But I've seen some very large that go up to over 500 newton meters.
Wow.
So there's some castings, some large castings for vehicles where they're using these things as like threaded inserts, and these they exhibit this kind of design. So even at a larger scale, it's possible.
Okay. Oh, interesting. So maybe we can chat a little bit about Atlas and Atlas Copco.
Sure.
I don't know if you know. Do you have how did Atlas get into tightening tools? Like, do you know the history, just out of interest?
Yeah, a little bit. So we really started as a pneumatic tool company. Well, actually, Atlas has several divisions. So we've got some different tooling divisions. We have air compressor division. I think the air compressor might be our biggest division. And so there's really several facets to Atlas Copco. So we can't really. I only know mostly about the tightening side. Yeah. But historically we were doing air assembly tools, and so before we really had these high tech DC electric tools. The air was king. So you would be really trying to transfer energy into the fastener, and the most efficient way to do that is with air pressure. It's fast, and it's a great way to transfer energy. And so at that point, you used like an air impact before, where you can feel the tool pulsing as you drive it in. So that was basically our starting point. There is creating the industry standard for an air tool for assembly. And then really, many years ago, before my time even here, right back 25 plus years ago, we were creating the first DC electric motor tool systems. So I have this is what the tool looks like now, but we've got a tool that has that has an electric motor in it. This is a brushless DC electric motor. On the back end of the motor, we're actually counting the angle with a sensor. It's an angle commutator that counts the angle. And then we have a transducer, a torque transducer here, that's actually measuring the applied torque to it. And then this tool, it has a telescoping end so it can follow the bolt down. This would be like for a fixtured application. So this could mount on a robot and it would come down and drive down and do a multi-tightening like that. A hand tool would look more like this, where we've got a battery here. This tool has an integrated controller to it. There's a trigger on here that you can pull and make this thing turn. But the same thing, we've got a DC electric motor, we've got an angle measurement, and we've got a torque transducer that's actually going to read the torque on the joint. So the challenge with the historical challenge is with air tools is that they didn't do a great job of reading the torque. Right? You could have a way to balance the energy transfer by how many times you were pulsing, but you couldn't read the actual torque on the joint. So not until we got into the area of the DC electric motor and the torque transducer were we able to control the tightening directly with a measured torque value. And that really lends itself into data collection. And now we're in a situation where we can do certainly all of this analysis in the background with software. We've got all kinds of software that analyze torque curves and create box plots and all sorts of things with this analysis. But just to simplify, measuring with torque and angle and having those two data points, you can get a really high quality, really good confidence in the quality of the tightening with just those two numbers. So the bolted joint really lends itself to being tracked. And I know you know better than everybody how important it is to collect data and do smart things with data. I think that's about half of the things I've seen you talk about, maybe more, is what to do with the data and how do we make smart decisions with the data. And so now what we're doing is this bolt lends itself to that. So there's lots of parameters that we can collect data on. So a little walk down the history. Sorry if that was a little bit of a windy road.
I think you did brush over the fact that you've got a wireless tool there. I know that it took a long time to get wireless hand tools onto the market. I mean, even today we have cabled hand tools, which is, I mean, if I think about it, that's all we knew for the last 15 years. And then all of a sudden, these wireless tools, battery-driven with Wi-Fi, have come into the market. Has made a big difference from an ergonomics perspective and a movability perspective. And I think it's been pretty awesome. I don't know if you could. Would you be able to sort of draw out a picture of? You kind of showed the motor, the transducer, the output drive that obviously gets cabled to some box. Just to kind of give the audience a view of the sort of main components of a bolting tool.
We can do that. Yeah.
Because I think that's often people just see the bolting tool at the end of the line, but there's quite a few things that happen upstream of that.
Yeah. So if we have a tool, let's see, you want like a hand tool, a cable tool, but like this style of system right here. We can talk about. Okay. So we have so there's a controller back here, and this controller is going to read torque and angle, and so we'll try a little isometric view here. So we've got a torque controller that this is plugged into the wall. And this is plugged into 220 volts in most cases, okay? And then so this is going to cable to the power tool and give it, so this has got the controller of the tool itself is taking place separately with this unit. And then we're cabling into here, applying DC voltage and current here. So we've got a torque tool with a motor, so it's going to have a handle on it with a trigger, and then a motor. So here's our motor here. On the back end of this motor, we're going to be measuring the angle with an encoder. And so that encoder is going to, and the reason it's on the back of the motor is because there's a planetary gear set here. So we have a gear set where we've got maybe a double or triple reduction. We get a lot of spinning here at the DC electric motor, Back here, we're measuring the angle. We go through a gear reduction, and then it comes through to where we have the torque transducer itself. And so the torque transducer actually has a strain gauge on it. So the strain gauge, we bond a strain gauge to a piece of steel, and it has, this kind of pathing of the wire. We put an electrical current through that wire. When the steel stretches, that path gets longer and the diameter of the wire gets thinner, and we measure that change in resistance. All right. On the torque transducer, these are set up at a 45-degree angle because what we're measuring is the torsional deflection of material in that tool. Actually, it's called the flexor section. It flexes, okay? And so we're measuring that twist. And so these strain gauges are mounted at a 45-degree angle so we can maximize the amount of deformation, deflection we have in that joint. Okay, then we go, so that's our torque transducer. Then we go into, in a case of a tool like this, we've got a bevel gear here. So this has got a right angle gear, and so this has got, a bevel gear like this, with a drive gear like this. And then here's my 1/2-inch square drive, or whatever size drive we have here, okay? So actually we want to be conscious of this, is that anything happening beyond that torque transducer, variation here, we have to have really high quality gears here to make sure that torque is consistent, because that's beyond the place where we're measuring. And oftentimes we'll see special applications where they're putting something like this on the end of a tool to get onto like a brake line or something like that. And if you've got something like this here, you're going to turn this thing and you're going to spin these gears like this. All of this is happening after the transducer, so we have to take extra care to make sure that we've got high quality components and we're doing the right maintenance cycles and things like that, because this is critical to making sure we're doing the proper amount of tightening to the bolt itself.
That just reminds me of an unfortunate situation where we had an offset drive. It wasn't for a brake hose, but for a bolt, to get access to a particular bolt on an axle.
Yep.
And the customer didn't do the necessary verification of the system. And months later, they had an issue in the field where a bolt came loose, and obviously trickling back down to where the problem was, it came down to the fact that output drive was starting to be more inefficient. And so the torque transducer was now measuring incorrectly, and they had a massive recall campaign. So I couldn't stress, as you have, the importance of that gear set after the transducer. Could be the make or break of a company, or a life for that matter.
Right. There's really some critical fasteners that we have to pay attention to, and that's part of why fasteners are ranked, in terms of how severe the problem is and how likely it is to happen. We do those analysis, and we come up with some results that say, this bolt is really important. This is where it really justifies having a high accuracy power tool and have the right process in place to make sure that sort of thing.
Yeah. Is that what you call that? If I remember, I think that's referred to as classes, right? Or categories.
So they'll put it in some kind of joint classification. Now, customers all have different names. I'm going to try not to. I want to be careful exactly how the words I use here, because I deal with so many different customers. But joint classifications.
Okay. Based on the criticality, also the consequence of what happens if it comes loose.
Yeah, so we do a failure mode effect analysis, right? So I'm sure you're familiar with that. We look at how likely the problem is to happen, and then how severe the problem is, and then we put some categorization on that. And so typically that drives the torque tolerance, is the primary driver there. So we're going to find the general category is going to be maybe anywhere from a plus or minus 50% to plus or minus 25%. So big torque range for those non-critical joints, right? Those could be anything from like, something where there's a lot other screws to take the load, or something where it's like it's really not critical. Say you have a plastic assembly and you've got 20 screws. It might work if 10 are tight, right? You know what I mean? So like a situation that certainly can happen, and those are the situations where you have a much lower accuracy requirement for the tolerance, because there's other screws to do the job, and that if one is not tight, then it's not going to have a huge impact on quality or safety. Then you get into that quality critical range where the performance, the tightness of this bolt is important to the how the performance of the product itself. So say I have a suspension making noise, right? Something like that, where it actually is affecting the quality and performance of the part. And those are going to be about plus or minus 10%. So when I say tolerance, I mean I almost always mean plus or minus when we're talking about this. So it's important to size the tool for that tolerance, and that tolerance comes from that DFMEA, or that classification process. And then beyond that, we may have plus or minus 5% on safety critical applications. Okay, and that's really forcing us to get the right kind of tool in place, and also potentially forcing us to record data. And I want to make this statement actually super clear. I never want to see a torque tolerance tighter than 5%. I see this happening, and I find no value in being tighter than 5%. What ends up happening is that you end up having trouble meeting that specification. And just like a dimensional tolerance, you wouldn't put an unnecessarily tight dimensional tolerance on something if it didn't add value. I see people doing this. They think a tighter torque tolerance adds value, and it doesn't necessarily. And tighter than 5% adds almost no value.
Yeah.
All right. If you come into a situation where you say, Jason, I found one where we should be tighter than 5%, I'm going to tell you, don't use torque as your control strategy. Use a torque plus angle strategy, like we talked about. That will give you a much more consistent clamp load. So the real reason I say that is, well, for one, I struggle with this on almost a daily basis. Customers putting too tight a torque specs on things and not seeing any real value out of it is because the friction variation is such a bigger player in the outcome of the variation of tightness that tightening up the torque tolerance doesn't mathematically actually improve the situation, because you're getting 25% variation from friction. 5% variation in torque is such a small amount of additional variation that it doesn't actually benefit. Yeah. So sorry, there's my tangent on torque percentage. Yeah. Never tighter than 5. You need a different tightening strategy. If mathematically you come up with that, you need to be better than 5. Yeah. But to answer your question about those ranges, to bring this back around to the tools, the customer is going to come up. They usually come to me with a torque tolerance. Sometimes when we write a torque spec, we'll recommend a torque tolerance for them. But what that ends up happening is they have to select a power tool that fits into that torque tolerance. And so there's another recommendation that we should make there, is that the tool itself should be more accurate than the process. And this is really true of any manufacturing situation, right? And so the accuracy of a tool like this is plus or minus 5%. Okay. So in this tool, this would really be appropriate for like a plus or minus 10% joint, because I can't take up the whole tolerance with just the variation of this, or at least I shouldn't, right? Because torque is one of those qualities that we have to, we can't check every part, because we'd be upsetting the bolt by checking it and doing an audit of that torque. So we have to prove the process is better than our specification. And so usually we target 1.33 or higher as a CPK value of a power tool. For that reason, we need a more accurate tool than the spec of the process. We could get into the weeds on talking about CPK and CMK and stats and stuff, but at the end of the day, we want a tool that's more accurate than the requirements of the process.
Yeah, I think to your point around the not more than or not better than 5%, I think comes down to inexperience and lack of education, which is why I think this kind of conversation is so important.
That's exactly what it comes from. It comes from things being tighter, right? Things being, they think tighter is better, because in some cases that's true. But really, tolerancing in general should be as big as the thing can be and do the job. Yeah. And so that's really the end goal.
Yeah. Yeah, and I think inexperience means that you over design. You put instead of a times 3 safety factor, you put a times 20, which
Yes,
then
yes,
has a
yeah.
negative impact at the end of the day, and because of inexperience at the end of the day, I think.
Yeah, absolutely. Yeah, yeah. So that's something we try to teach our customers. I actually learned early on, with the culture at Atlas Copco that there's really no sense in keeping information to yourself. It's actually best to share as much of the information as you can because it's to everybody's benefit the more they know about the process. And I think some people they feel like their value is like, I'm the best PLC programmer, so I want to be the best PLC programmer. And your best value, and generally speaking to everybody here, is to be the best teacher of how to be a PLC programmer and how to create a bunch of awesome PLC programmers around you that will not detract from your success in your career. And that's something I found is really one of the really good things from a culture standpoint about Atlas Copco is that I've been able to openly teach not just to our internal people, but to customers, right?
Yeah.
Situations like this, right? I'll tell you everything. There are no secrets to what it takes to tighten a bolt. The more people who know about tightening a bolt, the more likely they're going to buy our tools. So why wouldn't we have that attitude, right? Because we do have the best product in almost every case. So there's some really neat stuff we can do with this, and I'd love to take all the time we can talk to teach you about it. So that's cool from a culture standpoint to have that.
Yeah, absolutely. I think you've given such great career advice. The more people you can teach, the sooner you can move on and do new things.
Yeah, I noticed this from your videos too. Is that I think you have that exact same attitude, right? There's no benefit to keeping knowledge. And actually, I've noticed in the industry, I wonder if you notice this too, is that there's actually some loss of knowledge that naturally happens. That you think that the company's constantly building up their knowledge, but they're also constantly losing knowledge. Yep. And that's not so obvious until you see, whoa, we're making mistakes we've made before, right? These mistakes have been learned. These lessons that should have been learned already. That's something I see more and more.
I mean, to be quite honest with you, that's a problem we have in our company. We know how to tighten a bolt, but what that means is that there are a few individuals in our company that know how to tighten a bolt. And if those individuals leave, then that statement doesn't hold true.
Right.
So it's not we. There's about 3 or 4 people that know, and if they leave, then you can't say that. But you assume that the company knows, but it isn't. It comes down to some individuals that know in the company.
Right. Yep. Absolutely. Yep.
I wanted to just looking at the picture of the controller behind you. I think that controller does a whole lot more than just apply the right torque and angle and do the evaluation of the windows. I mean, simple things like calling different programs. I certainly want people to understand that when you buy a bolting tool, it doesn't just do one program or one setting.
Sure. Yep. Yeah. So the tool, the controller really is the core communication standpoint too. So when I program a power tool, I'm connecting my laptop using some software to actually program the steps within the process. So all of that communication standpoint is interfaced through the controller. This can communicate wirelessly through Wi-Fi or Bluetooth. There's 5G. There's a bunch of different ways to communicate. Now that we have, like you mentioned, the integration of the battery systems. This is really comes down to communication and how quickly we could make communications. That's why we're seeing so much more of this technology's advanced. But the controller itself can hold a huge number of different programs within it. It can call different programs in different orders. It can do automatic retries of things. The fixture tooling system too has got even more features. We can synchronize spindles, so we can do multi-spindle tightenings where we've got 30 bolts all being tightened at the same time. And then we can actually isolate different programs to run different things within each bolt. And we can say if this bolt fails, hold everybody, stop everybody, and just retry this bolt. And then if this is there's all sorts of configurable different things you can have, with interfacing with the controller. Let's say you have a multiple different bolt sizes. So as long as it's within the same range of the torque capacity of this tool, I can have a socket changer that automatically calls a different program for when I pull a socket out. It's like a block that's got the sockets that live in it, and there's a sensor under each socket, and it tells when you pull that socket out of there, that it calls a new program and can actually just start that part of the process for you.
Yeah, that's pretty cool.
This also communicates with guidance systems. So a big part of what we're doing with tools is putting some form of location onto the tool, and that can go. We can talk about that for a long time. There's you can have an articulating arm where you've got like basically an arm that has at each joint it has an angle encoder, so it can like basically GPS position the tool to where it is, so you can force the operator to do an order. You can actually there's optical things that we'll put a tag on this tool, and we use inline vision to know where that tool is in space. And so there's several options for putting this tool into the right order to making sure the operator is doing the correct process, and that all interfaces through the controller. So there's actually quite a bit happening there. So I'm glad you brought this up.
We've actually made an AI model of one of your Atlas Copco hand tools, and so we can track the position of the hand tool in 3D space. I'll actually share a video. If it's in a particular position, we can enable and disable the tool from a single camera. Like same tech as self-driving cars, so we're able to detect different objects in the scene, one of which is an Atlas Copco bolting tool, and I can then output coordinates of the position of the bolting tool without any tagging or anything on it. And then the system, the PLC or whatever it is that's controlling the station, can make a decision on enabling the bolting tool and calling the right program.
Yeah, there's a lot of options there to integrate the tool to the line to create that like total quality system. And I think that you guys see that in the lines that you guys assemble. I think you see the importance of the features that are built into the system to making sure that the bolt is tight.
Yeah, I think one of the things that I guess is maybe not the right conversation to get into, but I think the bolting controller is, as a system integrator, is now enabling us to do more from the controller than in the past. So maybe less done by the PLC, so I can reduce my overhead, both from a cost perspective and a training and programming perspective on the PLC itself, because a lot of the functionality has been taken care of by the bolting controller itself. So for me as a system integrator, it's better value for money. I was buying the bolting controller anyway, right? Like in the past, it's not so recent, but for example, controlling a socket changer from the controller had to be done previously by a PLC. Now I don't need the PLC, right? Yeah. So simple things like that.
We're constantly trying to add that sort of value into the system, right? To identify a need in the market and to respond with products and features. As a company, we're like the biggest budget for R&D around, so we're often the first ones coming out with this type of technology. And actually, this tool even right here, this is actually doesn't even interface with the controller. This has the controller functionality integrated and miniaturized into it itself. And so there's some interesting functionality we can see on a tool that's got an integrated controller into it, where this doesn't even need that separate architecture. So from a cost saving standpoint, it's even higher on something like this, because that controller's been integrated into the tool itself. And then on the fixtured side, we could have you could have this mounted on a robot, and then you could have the smaller controllers that are actually mounted to the robot itself. And you could actually mount that separately to the system to really create a really clean multi-head where we're able to do a lot of that happening right at the robot itself. So awesome. that sort of aspect has been thought pretty well.
Yeah, that's pretty cool. Maybe just staying with the actual, you had the fixtured spindle in front of you. I know that there's a difference in duty cycle between the hand tool and the hand tool and the fixtured spindle.
Yes.
Do you want to maybe talk through why that's important in selecting a tool?
Yeah, so a tool like this is going to run. And also not just duty cycle, but also like service cycle too. So this is a tool that's going to run 1 million cycles before its first service. And but we're talking about, usually these are in multi-spindle configurations, and we're talking about 480 volts into the controller, right? Operating the DC, three-phase DC or three-phase voltage coming in and running a group of these. And so this is going to have a much higher duty cycle, we're going to be able to run, a 3-second cycle time, and running this thing every 10 seconds, no problem, right? So usually we can produce quite a bit of parts on these. We've got some customers that have these out in the field that are producing we've seen many instances with over 10 million cycles on a tool like this. And so we're looking at high volume production. A fixtured tool like this running off a higher voltage is really the right bet. There's a lot more features to this system too, as to how we can program this. And these come in all sorts of different sizes, in upwards of 10,000 newton meters. We had a 10,000 newton meter version of this in the lab recently. And it was
10,000
about
newton meters.
10,000 newton meters. Yeah. So
what does it type?
So this is a 20 newton meter tool, and that's a 10,000 newton meter tool. So it's tightening a hydraulic cylinder together. So you see these big pieces of construction equipment, and the actual end of the hydraulic cylinder gets tightened on. But the thing is, this big in diameter, so it needs that kind of torque. But they get the value of collecting all the data from it and doing all of the features that are built into the system. So, before, where they're having a very manual operation with some kind of torque multiplier. I mean, 10,000 newton meters is crazy, because you think about how big of a wrench you would need for 10,000 newton meters. We're talking about a 10 meter long wrench, right, or bigger. That would be a tool that you couldn't even physically handle from a manual standpoint.
I'd love to see the fixture that holds that tightening tool and the part.
It has to be really strong weldments to hold this thing together, because it's there's lots of bolts to it too. So it's definitely those bigger torques are interesting applications.
Speaking of torques, you kind of walked me through your lab there, and obviously there's a couple of collaborative robots.
Yep.
I've been somewhat, to be honest with you, let me give you my bias. I've been somewhat skeptical about just using robots in general for tightening, because of the torque reaction that goes back into the robot. And obviously you can have a big industrial KUKA robot or a Fanuc robot, and really overspec it and tighten 10 newton meters. Obviously that's not a problem, but I've seen more and more applications where we're using collaborative robots, and because it can carry the payload, I don't think people have considered the impact of repeated torque reaction through the robot joints. What's been your experience with that?
So that's actually something we've been working with the robotics companies on. So they have the same question, right? Because the longevity of the robot. So in a direct drive tool, and most of these tools we talked about today are direct drive tools. When I say direct drive, like if it's putting 100 newton meters of torque on something, it's reacting with that same 100 newton meters something. If it's a hand tool like this, then that's going into me, right? Unless I'm on an articulating arm or something like that. But the robot's doing that job. And in the cobot situation, you've got a collaborative robot. That might be enough to trigger the robot to think that, hey, I'm hurting a person, so stop, right? They're sensitive to that. So there's that aspect of it as well, is that we want to make sure we don't trigger the robot to falsely trigger it based on torque reaction. And there's some options there to make sure the robot is where it needs to be, and then you can somewhat reduce the sensitivity of the those joints. But also in designing torque reaction end of arm tooling. So if you have a really high torque tool, you'll see it actually has what we call a reaction bar that comes off the end of it, and that reaction bar will touch off of an adjacent bolt, and it will take that reaction away from the operator and push an adjacent bolt, and then use that to tighten another bolt. The same concept can be used on end of arm tooling for a robot, but that gets into something that takes a little more finesse in the design phase, is because you've got to kind of preload that. You got to preload that socket to grab that bolt in the right place before you tell the robot to start holding position, or before you really start to apply torque to it. So you've got to take up that slot and get that thing lined up. So big picture, I think that there's going to see this in the industry more and more, is the use of both robotics and collaborative robots to do tightenings. But it's something that there's going to be some growing pains with. It's gonna need some learning curve, and that's why we've got 3 robots in the lab right now is for this exact reason, is doing feasibility trials for automation type of assemblies, and saying, can we understand the hurdles before we get this thing? We bought the wrong robot or we bought the wrong tool. Can we do some feasibility trials beforehand to understand what's happening here? And then the benefit of that is it dramatically reduces the risk from the customer to buying the wrong thing. We don't want to sell the customer the wrong thing ever. That's a bad situation for everybody, right?
Yeah.
And then on the back end, we've already done the analysis. We already have the program. And I'm big on if we can do something easily and give it to the customer and it adds value, why not do it?
Yeah.
Right? Like, I know how to program the tool. Why would I not give you a nice tightening strategy along with doing some automation work or something, right? I want to put error proofing limits in, right? I want to give you a strategy. When we talk about error proofing limits, 0 to 9999, right? That's the Atlas Copco version of wide open limits, right? I want your limits to be 35 degrees to 95 degrees, so that first bolt you tighten in the factory, you get some quality there. So we can add those things onto the tightening operation to really give the whole complete package, right? And really mitigate the risk for the customer.
Yeah, I like I said, I'm somewhat skeptical on using collaborative robots to tighten because they're not designed for the duty cycles like your spindles are.
Yeah, so that part, I mean, that's more of a question for the robot supplier. So I'm interested to hear you say that. I think that we see it a fair amount here. Like out in our shop here, we've probably got at least 10 collaborative robots with tightening tools on them. I think that the multi-spindles that are doing their own torque reaction probably mitigate that concern, but a single spindle tightening operation is something that's going to need to be understood long-term in the industry from robot maintenance.
We've been involved in replacing 2 different collaborative robots with proper industrial robots, big, more bulky, and it's just a mechanical fatigue. They worked well for a year and a half, and it's mechanical fatigue at the end of the day. I often tell people, I think you need to go and understand what holding 30 Newton meters actually feels like, because it doesn't sound like a lot, but until you hold a tool that's pushing you 30 Newton meters, you then have a sense of how much force that actually is on your body, and now we relate that back into a robot. Like you say, I think there's certainly opportunities, but requires some level of finesse in the design of the torque reaction bars and that kind of stuff.
Yeah. So one thing we pay attention to is which joint of the robot is being loaded. And so like just how like if you've got the 6th joint of the robot in this axis, and then you're tightening, you're mounting that here, and then you're asking, and then this torque reaction wants to go like this, that's the worst case scenario. So what we're trying to do is figure out the optimized angle where we're not in line with that last joint or the weakest joint. So there is definitely some design consideration that we've done there. Creating torque reaction it could solve most of that problem. So that's I think what I hear you saying is that we're trying to put a robot in place of the guy who's holding this tool. It's working him all day long. Well, that work didn't go away. That work is now going into the robot, right? And so that's really what it comes down to, is can we handle that same situation?
I think the opportunity lies in, Atlas Copco have got these articulated arms with the encoders in there to measure position. And what's really interesting about those arms is that you have a brake in each of the axes. So the moment it goes into position and you press the button, those brakes engage. I have the sense that I think the collaborative robot of the future that's for bolting needs that concept, where you have that
idea has been explored, and I think you're right. I've seen a solution that was presented, and it looks a little strange to see a robot and an articulating arm, doing the same task, but it isolates the function. So I think the idea is sound.
Or you put servo drives in your articulating arm.
Yeah, there we go. That's that. Now there you go. I haven't seen that, but I wouldn't be surprised if that concept hasn't been.
Because the articulating arm is taking up the reaction. It's designed for
that.
What it doesn't have is the movement, the automatic movement.
Right,
And I think it's
right,
easier to
right.
add in the automatic movement to that than the torque reaction into a robot.
Yeah, no, that's clever. I think that has some potential for the
Yeah.
future. In 10 years, we'll see what's out on the market. But
Yeah, for sure. So one of the questions I wanted to ask you when we were talking about bolting strategies is you talked about synchronous tightening. And earlier you
yeah,
showed, I think it looked like a camshaft tightening or a main bearing cap tightening.
yeah.
Why is synchronous tightening important? Or what is synchronous tightening and why is it
Yeah.
important?
So what we want to do is when we're tightening a multi-bolt pattern with multiple tools at the same time, we want to make sure that we've drawn the bolt down together and that we're snugging it together. And before we reach each step of the torque process, so we talked about a torque process being built in steps. And so in between each one of those steps, we have a sync point where we're going to wait for all the other spindles to tighten and then go together to the next step. And because we're generating more force than we realize with a fastener in many cases, even a small bolt, like an M8 bolt, will pick a car up right off the ground, right? We're generating thousands and thousands of pounds of force with a small bolt. So it's deforming the part. Also, as it's stretching the bolt, it's also deforming the part. It's important for the quality of the part in many cases to bring that preload and build it up together. And so the tools are synchronized in order to do that. So this is particularly important like on a cylinder head for an engine. If you were to do a cylinder head on an engine and you were to go to the service spec and you were to use a torque wrench in your garage, they would tell you to work from the middle and work your way out from the middle because you're actually deforming the material as you're tightening. A full synchronization is going to bring everybody down together and maximize the flatness of everything and the consistency and minimize the unwanted deformation of the parts during assembly. So the tools, but beyond that, we sometimes unsynchronize the tools in order to exploit characteristics, and that's where things get really fun in this lab. Is that we'll like the main bearing cap bolts, we will synchronize them and then unsynchronize them and check this bolt and then check this bolt and then bring them both together back for their final tightening in order to identify certain things that are happening in the operation. So,
Wow. I've never
that
heard
sort
about
of that sort of thing is what we really like playing around with in here. I'd love to tell you it's super scientific, but a lot of what we do is really trying different things and seeing what responds best to it. And if you've got the tools to do the job and the tools to measure the outcome of it, you can really set yourself up for success and do the best possible job of tightening.
Yeah, that's pretty interesting. So, and obviously, I'm assuming that the tools would be able to tighten to the snug torque, and even though one would, let's say, there's two bolts, the other one hasn't gotten to the snug torque, but the one that's gotten to the snug torque will wait for the other one to come, and then they'll kind of synchronize together and that kind of stuff.
Yeah, exactly. Yeah. So to say it the most simple way, let's say we're going to 100 newton meters with two bolts. We'll program them to do a high-speed rundown to say 25 newton meters, and then one of them is going to hit first. It'll sit here and wait, and then it'll come. When the second one comes in, then they'll all go to the full final torque.
Yeah.
And so bringing the synchronization aspect is really something that we do with a multi-spindle really well, and we can actually hold that torque through the process. So this one can actually be sitting here holding 25 newton meters while this one's waiting, and then it really benefits to the flatness of the part and the consistency of the joint bolt to joint preload during the assembly.
So just a couple more questions.
Sure.
We've used tightening tools to do some, let's say, applications that were not originally designed, or tightening tools were not originally designed to do. For example, when you're assembling an engine and you've fitted the main bearing caps, you spoke about that. We want to measure the friction of the crankshaft before we carry on the assembly process.
Yeah.
So we've used an Atlas Copco bolting tool, applied a torque process onto the crankshaft to see that it's actually within a certain range. Do you come across the use of your tightening tools for adjacent applications that are not tightening a bolt?
Yeah. So this is one thing that the lab here, we get involved in all those weird areas. So we get to see all of that, and it's so we call that torque to turn. And so we often during the engine assembly we have to index the crankshaft anyways.
Yep.
So you're going to put a servo motor on there one way or another. Why not put a tool that has the measurement ability and the communication ability to connect that data to the whole system? There's a ton of value there. So what we'll do is we'll actually do that rotational test here. We'll test the breakaway torque. So it kind of looks like this. We've got a same graph, but we'll go torque and angle here. So this is angle and torque, but you get a breakaway torque, right? And then you're going to see some running here, right? And if you're running the you're going to see you're going to want to set a window here for this peak torque, and then you're probably going to want this mean torque here to give you those that value of the average running torque. So these are all things we can program different steps of the process into. Is getting maybe your first step is an angle step, and then maybe this is maybe five revolutions of angle or something like that, where we've got quite a bit of revolution to really see what this torque is. So setting up tools is interesting for that.
We had a requirement. This is going back, I don't know, 7-8 years now, to measure torque to rotate on an engine crank. And we got that, let's say, what looks like a sine wave, and the customer wanted the peak and the trough result.
Yep.
And at that stage,
so
we couldn't get the value. So we actually exported the graph using XML and did further analysis on the graph to validate it. We got the average out of the tool. I think now it's pretty readily available to get the peak and the trough. But at that time was somewhat challenging.
Yeah, so we've developed special software for this type of analysis. So really anything that falls outside of the normal tightening, that's something that we'd often, if it's happening in North America, it's probably coming through this laboratory.
Okay.
So like one of the things is setting valve lash. So setting the valve position on an engine is something where we're using there's an adjuster screw and a lock nut, and we're setting a gap in the engine. We have a system that's actually looking at the traces and doing some adaptive type of strategies to the compliance of that entire system, and it's really adaptive to different variation of the incoming product, so we can set a perfect gap every cycle. So those types of things we're really setting position there. We are tightening the lock nut, but mostly what we're doing is setting the position. So there are definitely situations, torque to turn, valve lash, things like that. There we're setting, outside of the normal tightening the bolts and asking the tools to do things that maybe they weren't initially designed to, but we can handle it with software and make sure it can do different things.
That's cool. Jason, my last question is to not give away any trade secrets. Obviously, what does the future look like for tightening systems, traceability? Like if we had this conversation in 5 years' time, what do you think the hot topics are going to be?
Yeah, I think how we integrate the tools into different systems. I think the topic of Industry 4.0 comes up a lot in how we're making decisions on the data. So tools that will be able to collect data in better ways and in more adaptive ways, and being able to analyze full trace capability. That's something we can already do, but I think we're going to do more predictive type of things with that. So the integration of AI into tightening systems, into the monitoring systems, and using that to create smart tightening strategies and smart monitoring strategies, I think is going to be a huge area of growth. I think that there's always opportunities for new things with the tooling standpoint, or how to make the tool smaller, lighter, faster, right? Those sorts of things, last longer. Even those same principles within the service of, can we use AI to predict maintenance issues? Can we use it to predict maintenance cycles? Can we offer the customer a complete solution where they're top-down integrated from the tools themselves, the maintenance system, all of that. And then in addition to that, really integrating our expertise earlier upstream into the tightening, into our customers' situation, so we can help them before they have to design a joint to pick out a power tool and they're finding that they don't have the right tool available for the job. having some interaction with the customer even in an earlier stage where we can build that relationship and they can rely on our expertise and we can work together to come up with the right design that's designed for assembly. I think there's a lot of design engineers that need help with, that really need help with designing a tool or designing a product that can be assembled. And I think you
Yep.
see that from a
Yep.
standpoint is that you're designing an assembly line, and it's like, man, if we'd have just had this conversation a year and a half ago, and I know that's a long time ago,
Yeah.
but that's when that decision was made, and now we're dealing with the ramifications of the process. I think working collaboration with the customer and improving that relationship is something that we're going to see some big growth opportunity in the future too.
Yeah, I certainly agree. It's one of the biggest challenges we have, combining a sort of expertise that, for example, that you have with our design expertise, with our customers' product. That trifecta could certainly be much more efficient, because what happens is customer designs an axle, we get the project to build the axle line, we then come to you and say, listen, I need a tool to tighten that, and then we could have saved a lot of time and effort and money if we just move the bolt 1 degree another way at the design phase of the product. So yeah, I think that more collaborative approach between the various stakeholders in trying to get that product out in a good time, good quality, safe, etc., is certainly beyond just the technology advancements. I think is going to be critical and necessary for the future.
Yeah, absolutely. Yeah. I think, and this is what we're doing today, right? Hopefully we can get some good knowledge out there, so we can help people build better parts and keep their bolts tight, right? That's the goal at the end of the day. As I want to do whatever I can do to help our customers keep their bolts tight. So.
Jason, is there anything that you would like to include that I haven't actually asked you, so I can prompt you with any particular question that would benefit you and your potential audience?
Yeah, I mean, there's really a lot to say. We do quite a bit of training for customers, and I feel like we'd be getting a little off topic if we went too far in the weeds with specific things. But I think this is a good intro.
Yeah, maybe let me ask you so if people want to know more about tightening, or have a need within their factory, or at the design stage of a product, how could they benefit from reaching out to you guys?
Yeah, so really, first point of contact is their local Atlas Copco sales representative, and they can kind of guide you to what services are available. So our service team it goes way beyond just fixing tools, right? We have proactive services that are consulting at the design level. Right, so we can go in and consult at the design level to make recommendations, and I've built relationships with some of my customers where they'll just call me and have me sit in on a design review meeting, and say, hey, can you give us 30 minutes and give us some time here, and then we end up doing work with them in the past, but that relationship we can elevate to more of like a consultation role. And I think that there's a huge amount of value there. So really starting off with the sales contact and reaching out that way and talking about training and consultation stuff. There's definitely some opportunity there. There's a whole portfolio of services that we have that I think can really help the customers. And it's just a matter of maybe not everybody knows what's out there to help them, but we can really make things a lot easier and a lot more streamlined from a process standpoint.
Yeah, I think Atlas Copco is more than just a tool supplier, at least to us. It's so much more.
Yeah.
Helping us in the design stage, in the right programming strategies. It's definitely a partnership. It's not we don't buy components.
Right. Yeah, it's not really a catalog item, right?
No.
And if you look at it that way, it's really you're taking all of that burden on yourself to integrate everything perfectly. Working as a partnership is much more valuable, and I think that everybody wins in that way.
Jason, we could certainly talk for a couple more hours. I'm deeply passionate about ensuring the bolt stays tight.
Yeah.
But I wanted to thank you for your time and effort. Like I said, we could certainly talk for more hours, and I would definitely recommend anyone that's listening to this to go on one of the Atlas Copco training courses, because I think you'll get more than just about a component in a catalog. It's a deep understanding as to why tightening bolts are important. Thank you very much,
absolutely.
Jason.
Yeah. No, thank you. This has been great. Yeah, I'm sure we'll talk again at some point. But yeah, it's really good to kind of spread that message
Yeah.
and help everybody out at the same time. So
Thank you.
appreciate it.
Have a good day.
Yep. Awesome. Take care.